Next up, we have Jonathan Ellis. He's going to be talking about the large language models and vector search, particularly as it relates to the work going on in CEP 30. That's the Cassandra enhancement proposal for adding native vector search to Cassandra. Jonathan was the project chair of Apache Cassandra for 6 years, so good pedigree to come from. Good person to have chat talking to us. So yeah, over to you.
All right, thanks, Hugh. So what I'm talking about today is kind of a 101 level of why vector search is important and why this is the most exciting thing to happen to the industry in general in 30 years. That 30 years is actually almost exactly spot on, because the last thing we've seen that was this important was the web in the 90s. And this is at least as big. If you're here for the low-level details of how this works inside Cassandra, I'm going to be talking about that at the developer meeting, I think in just about a week. But today is more about at the user level, why is this cool? Why is this important? And why should we care? So just starting at the beginning, if you're, a lot of companies have been successful using AI to power their businesses. Netflix's recommendations, Amazon's recommendations, lots of instances of fraud detection. But all of those are kind of what I would call traditional AI development projects, where you have to you basically have 4 steps until you can have an API that you can provide your application builders, where you need to extract the features that are relevant to the prediction that you're trying to make. You need to train a model against those features. You need to deploy that model and set up inference services for that. And by the way, you already did the feature extraction once for the model training. Now you have to do it again, because the one you did earlier was done by your data scientists with batch-oriented tools. And now you need to figure out how to get the same data out of your real-time systems. So step 3 here, deploy and serve, that's the closest to being something you can do kind of off the shelf. But even that, there's still dragons there. Every other box here is hire a team of PhDs and it's going to take them weeks. So the main problems are really what I just said, that you need to hire very smart people. It's going to take a long time, and multiplying those first 2 factors together, it costs a lot of money. And so when you have something that's valuable but expensive, you tend to only apply it to places where you get that ROI, where it's worth the investment. And what's happened in the last couple months is that we're starting to see that you can throw a problem at a large language model, and it will do a pretty decent job at giving you a first cut at solving that problem. So we've all seen that with ChatGPT, but you can turn that into a general purpose machine for solving problems with the APIs that OpenAI, that Microsoft, that Google are providing. So the simplest API call from OpenAI takes just 2 parameters, a model and a prompt. And that's it. And there's more this is the problem-solving model. There's also a chat model, which allows you to go back and forth. And so you can have, just like with ChatGPT, you can respond to its previous answer, and it will elaborate on it. But the simplest version looks just like this. There's exactly 2 parameters. It's just that simple. So the way you build an AI project with large language models is write your prompt, give it to the large language model, and there you go. That's your API. And so, even with even with things that you might not think are well suited to this format, you can do it with, like, you can throw latitude and longitude at it, and it's like, oh yeah, I kind of know what those are, and get useful results at. I'm doing a sidebar here to talk about vectors, and I'm going to tie that into what we just talked about with large language models in just a second. When you hear people in the AI space talk about, there's a bunch of terminology that gets used that is actually, when you find out what it means, it's actually super simple. So one of those pieces of terminology is embedding. Embedding can be either a verb or a noun. In the verb form, it means taking text and then encoding it as a sequence of float 32 numbers, almost always float 32. And it can also be, as a noun, it can be the result of doing that encoding. So as part of building these large language models, the AI companies have created this kind of sub-project of embedding models that can take arbitrary text and turn it into a vector. And these are large vectors. OpenAI's most popular embedding model is 1536 dimensionality, and Google's is half of that. It's 768. So very large, which they need to be because they're trying to encode arbitrary human expression. The cool thing about vectors is, and this is not something that's newly relevant, this is like Amazon's been using cosine similarity in recommendations for 20 years, but you can trivially determine how similar two vectors are to each other by using cosine distance or dot product distance. And the output of doing that calculation is a single number that encapsulates how close these vectors are to each other. So the first obvious implication of this is that you can use embeddings to do semantic search. And in fact, you see products out there called, hey, we provide semantic search. That's probably what they're doing. Apache Solar's implementation, they call theirs neural search, which sounds cooler. It's the same thing. And so these embedding vectors can capture the distinction, the semantic differences and similarity much better than term-based search. So in these examples, I have one false positive. So the first one, if I'm searching for man and dog, I will get back both of those results, but they mean the opposite things. It's very different semantics. And then in the second and third, these are more of a false negative example, where if I'm interested in tourism, I will only get one. If my search term is tourism, I will only get one of those two examples back because they're using completely different words, even though they're talking about the same thing. And in the third example, these are related concepts. It's not exactly the same thing, but they're related concepts. And embedding vectors will be able to tell that these are semantically more similar than, for instance, either of those first two pieces of text when I'm looking for things that are related. So here's why this is relevant to large language models, because the large language models have a limited window of context that they can use to that you can provide in your prompt. And so, GPT-4, as powerful as it is, its knowledge cutoff is almost 2 years old at this point, and it's designed to be a mile wide and an inch deep. It's just a very general set of training data. And so this is the source of hallucinations that people talk about, because LLMs, this is less true with GPT-4, but it still happens. LLMs will prefer to make something up than to say, I don't know. And that's just kind of an artifact of how their training worked. But if you give them up-to-date information to ground them in reality, then that makes the hallucination problem, it almost completely solves it. And so then the question is, well, okay, how do I take from my set of data that I have about this problem, how can I distill it into the prompt that I provide the model? Because the prompt is limited to the token sizes that they give their sizes in tokens. And so those are 4,000 tokens for GPT 3.5, 32,000 for GPT-4, 8,000 for Google Bison. So these are all in the thousands of tokens, but not millions of tokens range. And roughly speaking, a token is 3/4 of a word. Like that's a good rule of thumb. So you're looking at 3,000 to 20,000 words that you can provide these models in the hopes of giving them enough information to answer your question accurately. And so what we want to do is that I've tried to illustrate on this slide. I want to pull out the most relevant information from my database and put that into my prompt. The way you do this is you encode your query with the exact same embedding model that you encoded your data with, and then I can perform that similarity search between the query and the data, and then get back and you can say, I want the 10 most relevant, the 100 most relevant, and then you just go through that list in order, and you put them into your prompt until you run out of space. So if your first two most relevant pieces of information are 2,000 tokens put together, you have room for another one. You add in that third, and so forth. So if I have this large language model and I'm combining it with vector search to prevent hallucinations and get more accurate answers, this literally lets me build an AI application 100 times faster than the traditional workflow. Maybe 1,000 times. Like it really is 2 to 3 orders of magnitude faster. And that's why this is so interesting and why everyone's excited about vector search all of a sudden. Now, it's true that with the custom model, you're probably going to get more accurate results, higher throughput, lower latency. It's going to be cheaper. You're going to be able to run it locally or offline. That doesn't mean that if you want any of those bullets, you have to go to a custom model. Here's what I mean. A guy named Alistair wrote up a great case study of doing this. And basically the approach is you can use in a slow, expensive, but accurate language model like GPT-4 to help you train a smaller, cheaper, faster language model, potentially based on open source, that you can run locally or offline. So if this approach works at all with GPT-4, you can usually distill that to fine-tune a cheaper model that's customized for your problem. So you can absolutely start with that general purpose off-the-shelf language model, and then staying within the language model and vector search paradigm, get better and faster and cheaper results. So my take is you should always start with the large language model and vector search paradigm when you're building an AI application today. And you can iterate on that. You can, this is called, one of the pieces of terminology that you'll hear is zero shot and few shot. Zero shot means, here's my question and I expect you to answer it. Few shot means here's my question, and I'm going to give you some examples of similar questions and correct answers. Now, based on that, I want you to answer it. So that's what that means. Few shot means adding examples. Or you can try switching from that model and prompt API to a chat-based API and iteratively refine what the model outputs. So you should only go back to that traditional model of feature extraction and model training and so forth once you've exhausted simpler approaches and it just doesn't work. So vector search in Cassandra. Here's what that looks like. We have almost completely finished the ticket for adding the new vector data type. The syntax is finalized, and this is what it looks like. I put it in bold that you have a vector of a simpler data type and the number of dimensions of the vector. And then you can create an index against that column like any other column with storage attached indexes. So queries look like this. First, I can say, I want you to give me the rows ordered by their similarity to my query, which is marked by the bind variable question mark. And I want you to search everything, like all the rows. And so that's going to do a scatter gather across the cluster. And so each node is going to order its results locally, and then the coordinator will have to combine them and then reorder them. So that's relatively expensive, but it's supported. The Cassandra answer to how do I scale is partition your data, and this composes with a partition key. So that's going, now this is going to scale as you add nodes to your cluster if your data fits that model. The other cool thing that you can do is that you can combine it with other SAI indexes. And so this includes arbitrary nesting of Boolean predicates like I've illustrated here. And then once you've got SAI computing the intersection of that, and then you can say order by vector similarity. So all of those work. So where we are is the CEP30 is accepted, and this code is in open beta. You can use it today in DataStax AstraDB, which is our hosted Cassandra. So that's where we are. I encourage you to try it out and give us feedback. And with that, I'll turn it back to Hugh.
Thanks so much, Jonathan. That was fantastic. And that's it. Thanks very much. Great to have you all here. Thank you very much, everybody. See you next time. Bye.